Hey, hi everybody. So now we're going to start a new section. It's 4.4. It's called Curve Sketching in your textbook. And what I like about this section is there's not really anything new so far in this section. It's kind of just bringing everything together and tying it all together. And we're going to use everything we've learned from calculus to your algebra classes in order to be able to graph functions. And so the way that we usually do this is that the best way to do this is to know certain things about your function. For example, the things that will help you graph the function, and I'll list them out in order of 1 through 9, is 1, to know your domain. So you always want to know your domain. And so what do we mean by your domain? So by the domain this is something I ask you all the time, saying, hey, what kind of function are we dealing with? Because that can tell us a lot about a function, right? So it's always good to know what's going on with the domain of your function. So for our domain, we want to say that this is to determine the values of x for which f of x is defined. And we always have a good habit of doing this, and so far we've had a good habit of doing this in our class. So that's something we need to keep doing, especially if we're interested in what the function looks like, because we have to keep in mind what can we plug in for certain x values. And remember that if you have a polynomial, it's always all round numbers. If you have a rational function, then you have to be a little bit more careful. Also with your trig functions, you have to be a little bit more careful. So it's good to keep all these in mind. And so another thing that's going to help us is the intercepts. So for the intercepts, remember that our intercepts is where they either cross the x-axis or the y-axis. So for our intercepts, recall that for our x-intercept, for example, we always set our y equal to 0, or in this case, f of x equal to 0. And then we will solve for our x values. And so you'll have an ordered pair where you have some value for your x value, and then your y value will be forced to be 0, or your output will be forced to be 0. Okay, so that's always something to keep in mind. And then once you know this information, once you know your x-intercept, it's good to kind of put that point into your function, and we'll do an example of all of this. But this is typically the way that you'll go about graphing functions. And then the next thing you'll find is your y-intercept, and remember, for your y-intercept, you always set x equal to 0 or your independent variable equal to 0. So you'll set x equal to 0. Or your independent variable. So if you're using thetas, and you'll use theta as 0. And so you'll always have an ordered pair, 0, comma, f of 0. Okay. And then the next step is to always think about symmetry. So when we think about symmetry, remember that we kind of mostly dealt with this in 125, and we briefly went over this at the beginning of this course. And when it comes to symmetry, we want to know, is our function even? So we want to know, is our function even? Is it odd? Or is it neither? Is it neither? And another one to think about also is periodic. And so even functions, remember, those typically happen if I plug in my value f of x, f of negative x, I end up with my same function f of x. For my odd function, if I input f of negative x, I will spit out negative f of x. And neither would be if none of those happened. But for periodic, The ones that we've dealt with more that are periodic are usually our trig functions. So for periodic functions, those are our trig functions. And we know those are periodic because, for example, our sine graph has a period of 2 pi, our cosine function has a period of 2 pi. So it's good to keep those in mind. What kind of function are you dealing with? So that when you graph it, it's really easy to graph. So that way you can maybe just graph one period of it and you know that it's going to repeat on the second half of the period and you don't have to keep drawing them over and over again. Or if you wanted to draw 2 periods, you just basically copy and paste. But then also our even function tells us, hey, are they both going the same way? Are they going the opposite way if they're odd across the origin? So those are all very helpful tools for you to help you graph our function. Now our fourth step here is to look at our asymptotes. And or our holes of our function. And so for this, there's actually many ways that you can actually think about this. One, you can think about it in the calculus sense that we've talked about, where we know that we get horizontal asymptotes. Actually, I'm going to start with the vertical asymptotes first. So for example, vertical asymptotes. So when do those happen? So typically, if you have a rational function, you set the denominator equal to 0. Then the thing that makes your function undefined in the denominator will usually cause a vertical asymptote. Not all the time, but it typically does. And if it cancels out with the top, that means that you have a hole or a removable discontinuity. So remember that a vertical is the line x equals a. But the way that we talked about this in our calculus class is we said that if we take the limit of a function as x approaches a from the right of f of x, if that goes off to either plus or minus infinity, or if we take the limit as x approaches a from the left-hand side of f of x, and it approaches plus or minus infinity, then those will cause vertical asymptotes. And that tends to really happen for our rational functions when we have things that are undefined. So for example, if I have some random function f of x, and I say that it's the function 1 over x, let's say minus a, right? We have this intuition or this gut feeling that we know x can't be a. And so then we have to do a little bit of investigation and say, hey, is it a vertical asymptote? Is it a removable? What's going on? So you can either take the limit to find out whether it's a vertical asymptote, or you can use your algebra skills and know that because it didn't cancel out with the top or the bottom, with the top, then it's going to be a vertical asymptote. But if I had the case where I had an x minus a at top also, then that a would now be a hole and will be called a removable discontinuity. So these are all going back to our algebra days and our algebra skills. So there's two ways you can find your vertical asymptotes. One, using your limits, or two, using your skills from algebra. Now let's talk about the horizontal asymptotes. Now for our horizontal asymptotes, what we can do is, you've learned from your algebra class that our horizontal asymptotes are the line y equals, and I'm going to go ahead and call them y equals L1 or y equals L2. The reason I'm calling them this is because for notation wise, I'm going to show you how we find horizontal asymptotes. And the way we find horizontal asymptotes, remember that a horizontal asymptote is if we have some function like this, then this is considered a horizontal asymptote right there. And that's because let's say the function looks like this. As the function approaches positive infinity, it approaches this line. Let's call this line L1. So our horizontal asymptote is on a y equals line. It's a horizontal line, and that line is always on y equals. So what we want to do from there is, one way that you learned in your college algebra class is that you have a horizontal asymptote if you have a rational function, if the degree is greater than the bottom. If they're the same degree, then you take the leading coefficient. So you can observe it that way, or you can use your limit notation in order to identify where your horizontal asymptotes are happening also. And so this involves a little bit of calculus and a little bit of derivatives, because in order to find the horizontal asymptotes, right, we want to know what happens to the function in the long run. So in the long run going to infinity, or in the long run going to negative infinity. Is it shooting off forever, or is it kind of like settling on something like the line y equals L1 or y equals L2? We don't really know. And so that's what we're going to investigate. And so the way that you do this is that you can take the limit you are going to take the limit as x approaches infinity of f of x. And if this approaches some line y equals L1, some value L1, then that's going to be a horizontal asymptote. Also, if you take the limit as x approaches negative infinity, so the long run now on the opposite end, going to our negative numbers, if that limit equals L2, these are going to be your horizontal asymptotes. And these are only your horizontal asymptotes if these limits exist. So if the limit exists. So you don't always have horizontal asymptotes. It's not always the case you have horizontal asymptotes. So basically, we will have horizontal asymptotes is you can use a little bit of calculus in order to determine whether you have horizontal asymptotes, because we want to know what's happening in the long run as x goes to infinity. And we want to know what happens in the long run as x goes to negative infinity. So if you take the limit as x approaches infinity and you get a value, let's say L1, or if you take the limit as x approaches infinity and you get a negative infinity and you get something like L2, then those are your horizontal asymptotes. If those limits do not exist, then you don't have a horizontal asymptote. So for example, you shouldn't expect to get a polynomial function, a quadratic function, to have horizontal asymptotes. That's not going to happen for a quadratic function. So also, you don't always have to check this. If you know ahead of time that your function does not have horizontal asymptotes, then don't do it. Like don't get a parabola and then start trying to take and find out if there's horizontal asymptotes. Yes, it's good practice, but it might not happen. And actually, you should know that for a polynomial or a quadratic, it's not going to happen. It usually tends to happen for rational functions or logarithmic functions. So just be mindful when you're finding your asymptotes and ask yourself, is it realistic for this function? And that'll help you when you're graphing them a lot. Now, the fifth way that we can do it is we can find our critical points. And recall that previously we said that we can find our critical points. One way is to take our derivative and set it equal to 0, and the values that satisfy that are our critical points. So the first way we do it is by taking a derivative, set it equal to 0. Another way a critical point can come up is by finding where the derivative does not exist. So it also happens where f prime of c does not exist. And remember that it doesn't exist where the function is discontinuous, so that's why it's always good to look back at the original function and go, okay, my function is not continuous there, and so therefore I can't take a derivative there. Or for example, remember that in sharp corners, you can't have the derivative, so that was on your quiz. And that's why I put it on there. I just wanted to see your thought process on absolute value, because remember that that sharp corner of that absolute value, your derivative doesn't actually exist. So x equals 0 was a critical value for that. Okay, and so that's the way we would do that. And then our sixth way that we can graph our function is by finding our local extrema. So, by finding our intervals of increasing or decreasing. And remember that when we find our intervals of increasing and decreasing, we can basically do step 5 and 6 basically simultaneously, because it doesn't really matter what order you do 5 and 6 in. Typically, I probably should have put 6 first and then 5 first, but it doesn't really matter because you kind of do those steps at the same time. But knowing where your function is increasing and where it's decreasing can help you definitely graph the graph. And remember, the way that you do this is by partitioning the real number line where the critical points are. So using the real number line. So once you find that real number line, you partition it into where your critical points are. So if you have one critical point here, another one here, and another one here, it doesn't have to be in any specific order. Remember, it's just from decreasing to increasing. Then you can tell where the intervals are increasing and decreasing. And then from there, we're going to find our local extrema. So our 7th step is to find our local extrema. And remember that, and I think there was a little bit of confusion here, is local extrema refers to your y values of your function, not your x values. Your x values of where those extrema happen are our critical points, not your local extrema. Your local extrema is, for example, let me do a small example here and then I'll erase it. But for example, if you have a function over here, this extrema, let's say that this point here is, I don't know, 7. My local extrema here is 7. It so happens to happen at, let's say, our x value 2. So our x value 2 is our critical point, but my extrema is 7. So I put 2, but it's lagging a little bit, and this is why I decided to do YouTube videos, but it's still lagging, so whatever. Okay. So I just wanted to clear that up. So for example, here, my x value is 2, which is my critical value because it's my value where I'm looking at, but my extrema is definitely 7. And the same thing if you have a minimum. So just keep that in mind. So how do we find our local extrema? You can do that using your first derivative test. So you do your first derivative test. Or you can do your second derivative test. And remember, you always plug these values, your critical values, in back to the original function. So don't confuse that with plugging it into that derivative. Okay. And now our 8th step is to find our concavity. And this is important because we want to know what the shape of the graph is looking like so that we're able to graph it correctly. So is it concave up? Is it concave down? Is it making a happy face shape? Is it making a sad face shape? All these things are good to note when you're graphing functions. So remember that in order to find the concavity, we always work with the second derivative. So sometimes it's nice to find your extrema using the second derivative, especially if you know you're going to have to graph the function, because you have to find the second derivative anyways. So that's good practice. And so you basically just find your f double prime of x, and then you set it equal to 0, and those values of where it's set equal to 0, or where, so you set f prime of x equal to 0, and the values, this, I said this kind of weird, but where your c values, or where f double prime of c does not exist, then those are going to be points of inflection, but you still have to test them because it doesn't always happen where it changes inflection there. And we've seen some examples of where that happens. So, or where f double prime does not exist. So those are the points you need to test. So you need to test these values. So whatever comes out, so whatever c values come out of those, you need to test them. And then your points of concavity. This kind of goes along with part 8, are your points of concavity. And remember, this is reporting that ordered pair, your x comma y of where that point of inflection happened. Because when you set the second derivative equal to 0, you're basically getting what's called a critical number, or a critical value for the second derivative and for your concavity. And that helps you identify where it's happening, but you want to know exactly where it's happening in order to graph it. Then you would need to plug that back into the original function. So here you want to actually determine, let's see that, determine if there is change in concavity. Because it doesn't always happen. You don't always get change in concavity when you get those points. We've seen examples where that happens, and we'll do maybe one later on. And so then in order to do your curve sketching is you'll take all of our steps from 1 through 9, and you'll use those tools in order to sketch your graph. Now, you don't always use all of them, but it is helpful to have those in mind. So like, think about what my domain of my function is. Like, you might not need to write that down each time in order to help you graph it, but it's a good tool to keep referring back to and knowing what tools you have in order to graph it. So let's go ahead and do an example. I said I was only going to do one, but I think I want to do a really simple one just to get the point across. And then I'll do a little bit of a harder one where we have to use a little bit more of these other tools, because half the time you'll use them, half the time you won't. And I'll show you exactly what I mean by that. So I'm going to do a really simple one that I'm sure you know how to graph, but I just want you to understand how to actually do this. So let's do an example. Let me make sure this is showing up. Cool. Let's do an example. So I want you to sketch f of x is equal to x to the 4th minus 4x. Okay, so I'm going to sketch this using the tools I just gave you. You don't need to write this down each time, but before I start graphing something, I always just start to make a little xy value, xy table on the side, just so that I can graph it as I pick up my information. So my first thing is, remember from before that my first thing that I want to look at is what's my domain. So You might not need to write this down each time, but it might be helpful. In this case, my domain is all real numbers. It's a polynomial. So I know that by looking at the function that it's a polynomial of degree 4. And so my domain is going to be all real numbers, which means I'm going from negative infinity to infinity, and there's no breaks in the graphs. So it's good to keep that in mind. And now my second step is to actually look at my intercepts. So we're going to go ahead and look at our intercepts. So we want to look at our y-intercepts and our x-intercepts. And sometimes we have y-intercepts, sometimes we don't have y-intercepts. Sometimes we do have x-intercepts, and sometimes we don't have x-intercepts. And that's why it's good to know if it's ever going to cross those values so that we can start plotting them right away. Okay, so go ahead and actually, good idea, pause the video and find your x-intercepts and y-intercepts, and then meet me back here so that we can do them together. So my x-intercepts, remember, so to find your x-intercepts, you always set y equal to 0. In this case, we're going to set f of x equal to 0. So here we set f of x equal to 0 from our algebra class, and we get 0 is equal to x to the 4th minus 4x. I can factor out an x, so then I get 0 is equal to x times x cubed minus 4. Perfect. And so then I get two x-intercepts. I get x equals 0, and then I get x cubed minus 4 equals 0, which means that my last x-intercept is going to be, I'm going to take the cube root of both sides, just quickly doing some algebra. So x equals the cube root of 4. So I have two x-intercepts from here. So my x-intercepts are actually 0, 0, and then 3 root 4 over comma 0. Okay, so what does that mean? So the cube root of 4 is a pretty small number. And so what we'll do is we'll start graphing this. So we know that we're going to actually hit the graph at 0, 0 already, so we can already use that tool to plot that point there. Then we need to plot the cube root of 4. So how do we plot the cube root of 4? So sometimes it's a good idea to kind of just guess a little bit of where it is. Remember, your graph's not going to be perfect, but just to guess where it is. I probably should have picked a graph that was a little bit nicer where you actually had a set x-intercept, but that's fine. We can always just graph it. So let's go ahead and put that here, and let's make this is going to be the cube root of 4. So we're going to say that it lives right there. Okay. Now our next job is to find our y-intercept, and our y-intercept is easy in this case. So remember, for your y-intercept, what you want to do is set x equal to 0. So we set our x values equal to 0, and when we do that, we get, well, let's look at our function. I plug in 0 into here, our x to the 4th minus x times 0. I just get 0, so my y-intercept is just 0, 0, which is expected because my x-intercept was 0, 0, and that hits both. That's the only place where it hits both the x-axis and the y-axis. Only place where that happens is the origin. So I did expect that to happen. So these are our x-intercepts and our y-intercepts. And so now I want to talk about symmetry. And so that, remember that for symmetry, we want to know if it's even, odd, neither, or periodic. It's not going to be periodic because we're dealing with a quadratic function. A polynomial function. It's not quadratic. We don't have a trig function where it has set periods. So we don't need to worry about that being periodic. What we do need to worry about is, hey, is it even or odd? Because if it is, then I know how to graph. It'll help me graph the function. So remember that in order to determine if it's even or odd, we'll go back to our function here. And we'll say, hey, if I plug in f of negative x, what do I get? Am I going to get back sorry, it went away, f of negative x, am I gonna get back negative f of x or positive f of x, or neither? In this case, if you tried it on your own, you wouldn't get either because this part of my function is even and the negative 4x of my function is odd. So I actually have neither, so there is no symmetry here. So we'll say that there's none. Okay, so for our symmetry, we had none. Perfect. And fun fact, I had to pause the video for a long time because my internet, or I don't know what, is so dumb right now. And it was just lagging and I'm so over this. So hope you guys are having a better time where you are at with your connection because I'm over it. Okay, so the fourth thing we need to look at is to see if we have any asymptotes. So we're gonna look for our asymptotes / our holes. And like I said, again, with this function, we're dealing with a polynomial function. There's no asymptotes or holes because it's continuous everywhere. So for this one, there is none. And then for the fifth one, we can find now our critical points. Now, in order to find the critical points, we need to take the derivative of f of x and set it equal to 0. So go ahead and do that. So the derivative of f of x is 4x cubed minus 4. So hopefully everybody got that. And now all we have to do is set it equal to 0 so that we can find our critical points. And since our derivative here is just another polynomial, we don't have any instances where our function f prime of x is undefined, so we don't have to worry about getting any critical points from our derivative being undefined as well. So then factoring out that 4, we get x cubed minus 1 is equal to 0. So this leaves us with x cubed minus 1 equaling 0. So we get that our critical number here is just x equals 1. So this is our critical number here. So this tells us that at 1, we either have a minimum or a maximum. So somewhere around here in this area, we're going to have either a minimum or a maximum. And now what we want to check is our intervals of increasing and decreasing, because we want to know, is it increasing here? And if it is, sorry, I don't know why it's not showing up. Is it increase? I'm so over it. Okay, whatever. It's not. Okay, there it is. Okay, we want to know if it's increasing here, because if it is increasing here, then we'll have a maximum value up here. And if it'll show up, that would be great. Yes. But if it's decreasing here, then we're going to end up having a minimum value right there. Okay, so our sixth step to do is to find our intervals of increasing / decreasing. Okay, I'm going to have to edit this video so much because you don't even know. There were so many points where it did that, and I was just over it. Breathe. Okay, so to check for our intervals of increasing and decreasing, remember we test this on the real number line. And so for our real number line here, we only had one critical value, and that critical value was 1. And we didn't have anything else. And so we only have to check before 1 and after 1. So we'll check that in the derivative. So go ahead and pick your nicest number that you would like. I would pick something like 0 and maybe 2. And we'll plug that into our derivative here and check to see if it's increasing or decreasing. And if I plug in 0 into this whole thing, this will go away, and I'll just be left with that positive -4 there, so that means it's negative here. So that tells me I'm decreasing. Now if I plug in 2, plug in 2 into here, is going to be a really huge number, -4. That's just a positive number. And so that tells us that we're going to have a minimum here. So at 1, we're going to have a minimum. And so what does that tell us about our graph? It tells us that, hey, we're decreasing from -infinity onto here, right? Because if we write down our intervals of decreasing, we're going to be decreasing from -infinity to 1, and then we're going to be increasing from 1 to infinity. Okay. Now, I know I'm going to be increasing from 1 to infinity, so I know that from 1 to infinity, somewhere around here, I know I'm going to have a minimum, so I'm going to go down and then go up. But now I have to figure out where is that minimum happening. So now in order to find that minimum, we are going to look for, and let me try to stay on this same page, we're going to want to find our extrema. And so now that we know that our critical number happens at 1, to find our extrema, all we have to do to find extrema, we're now going to plug in our critical value into our original function. And so remember that our original function is up here, which is x to the fourth minus x times 4 minus 4x. That's wrong with me. And so then we plug that in. And so you would plug in 1 into this. And then you'll end up with -3 because you'll be -1 minus 4. That's -3. So our local extrema happens at 1, -3. See how it's lagging? I'm so over this. Okay, it's fine. I'll get over it. Okay, so at 1, I go down 3. So my number line's not that, my graph is not that pretty. But that tells us that at 1, 3, now we have a minimum value. And so maybe I drew this kind of ugly, but now that we know that, we already know what the shape looks like. And in reality, we don't have to go as far as to find the concavity, but I just want to practice that for a second. So let's find the concavity of our function and determine whether our shape of our graph is going to be concave up or concave down. Now, by the look of what's going on here, it looks like it's going to be concave up. But you know what? Let's just double check with taking our derivative, our second derivative. So let's check for concavity. Okay, so now we want to check for concavity. So to check for concavity, all we have to do is take a second derivative. So love this example because it's super easy, just to get the point across. So our first derivative was over here. And so now what we want to do is take the second derivative. So we'll just take the derivative of this. And that's pretty simple. Our f double prime of x is going to end up being 12x squared. And remember that we want to know when this equals 0. And so that happens only if x is equal to 0. So we now need to test our point of inflection here. So in order to test it, we do the same thing like we would test to see if something was an extrema. And so now we do our real number line and test on the second derivative on this side and then on this side. Okay, it's working. Okay, and we test on the second derivative, so this will be easy. If I come over here, right, my second derivative is always going to be positive, so no matter what I put in here, it's always going to be positive. So if I plug in anything before 0, so if I plug in something like -1 squared, that's +1, multiplied by 12, that's still going to be positive. So on this interval, it's positive, and so that means it's concave up on this side, sorry. We're not talking about intervals of increasing, decreasing. Do the same thing here, no matter what, it's still going to be positive. So because it's still going to be positive, so here let's say I plugged in -1, and here I plug in 1, it's still going to be positive. It's concave up, which is what we expected by the look of this graph. We can already tell it's going to be that U-shaped graph. And so this tells us that our graph is looking like this. Oh. Sorry, it's so